Welcome back. In this video, I'll walk through a proof of Theorem 1.9, whose claim is that every graph of order n and size m, at least n squared over 4, contains a triangle. But before I do that, I want to talk about why are we talking about triangles here? Where does triangles come from? The idea here is if a graph contains a triangle, then it's not bipartite. And one way we can see this is if a graph contains a triangle as a subgraph, so here we have a triangle in the graph, and maybe there's some other vertices over here that are adjacent to each other, maybe adjacent to some of these, but as long as we have a triangle in the subgraph, and we want, and if we claim it is bipartite, what we would have to do is split up the vertices into the two partite sets. When we get to the triangle, we would have to split these three vertices into two sets so that two vertices in the same set are not adjacent to each other. So I have these three vertices I want to split into two sets. Necessarily, one of the sets will get two of the vertices. And no matter how I pick those two vertices, maybe I pick this one and this one, doesn't matter how I do it, they'll be adjacent to each other. And so they can't be in the same partite set. And so this is an argument for why if G contains a triangle, then G is not bipartite. And so if G is bipartite, it necessarily does not contain a triangle. Now we know from Theorem 1.8 that every bipartite graph has size at most n squared over 4. So if the size of our graph is at most n squared over 4, it's possible that we don't have a triangle in the graph because we know there's bipartite graphs there. What this theorem is getting at is that if our size is bigger than n squared over 4, then not only are we not bipartite by Theorem 1.8, but also that we contain a triangle. So there's something going on here between bipartite graphs and existence of triangles in the graph. This will get fleshed out a little bit more as we progress through the book, but for right now we can prove this. That if our size is at least n squared over 4, then we can contain a triangle. Or, I mean, strictly greater than n squared over 4, then we contain a triangle. So this is an interesting proof technique. It's sort of a combination of proof by contradiction and proof by induction. So what we'll start with is just establishing a base. I just want to say that for some small graphs, this theorem is true. So the smallest ones we should consider here is n equals 3 and n equals 4. So if n equals 3, then what's my number here? N squared over 4, then ceiling or floor of n squared over 4. So that would be 9 over 4. That's 2.25. That's 2. And so m would have to be greater than 2. And since the order is 3, the most number of edges I can have in the graph would be the complete graph would be 3. So in this case, m is 3. And there's only one graph that satisfies this, namely the complete graph of order 3, which is itself a triangle and therefore contains a triangle, right? This is a subgraph of itself, and so it does contain a triangle. If n is 4, so going up to the next level, if n is 4, then we would have n squared over 4, floor of that. That's 16 over 4, that's 4, would be 4. And m, so the size of the graph has to be at least 5 in this case. So is there any way to build a graph of order 4 and size at least 5 that does not contain a triangle? Well, we'll have to have at least a couple edges, and they'll actually have to be, maybe I can put these two in. There'll have to be another one. We need to somehow get 5 edges in here. If I can't choose this one or this one, that would produce a triangle. So I would have to put this one in here. I'm up to 4 edges, but now no matter what I do, I would have to put one of these edges in there, which would then form a triangle. So no matter what I do, if my size is at most n squared over 4 and my order is 3 or 4, I have to contain a triangle. So this kind of serves as our base. What we're going to do now is we're going to assume that the statement is false. We'll assume n is greater than or equal to 5. So we can assume n is greater than or equal to 5. And I'm going to assume the statement is false. Namely, there does exist a triangle-free graph without a triangle, graph of order n and size m at least n squared, or greater than n squared over 4. Right, so this would be a counterexample to the theorem. If such a graph existed, this would be a counterexample to the theorem. And since we already have this base established, we can say there's some smallest counterexample. We know there's at least, we're assuming there's at least one counterexample. There could be others. Of all of the counterexamples, like this one, we're going to select one with the smallest order. So of all graphs that satisfy this, of all such graphs, let G be one with smallest order. So the smallest number of vertices. Of all the counterexamples, we'll pick one that has the smallest number of vertices, and that's going to be G. The idea here is I'm going to use this to find a contradiction, right? I'm assuming that the statement's false. Namely, there exist counterexamples. I'll pick the smallest one, and what I'll do is I'll take this smallest one and I'll produce another graph that satisfies the hypotheses, namely that its size is at least its order squared over 4, or strictly greater than its order squared over 4, that's also triangle-free, which will contradict the fact that G is the smallest counterexample. So that is, there can't be a smallest counterexample, and so there can't be any counterexamples, is the idea behind this proof technique. So it's sort of a proof by contradiction, sort of a proof by induction, but let's keep going with this. So G is this graph of smallest order, size m, strictly greater than n squared over 4. So since m is greater than n squared over 4, we can assume there's at least, and n is greater than or equal to 5, we can assume that there's at least one edge in G. That's sort of not too hard to find. So I'll say let uv be an edge of G. So I have these two vertices u and v in the graph, and there's an edge between them. And I have some other vertices in my graph, right? I could have some other ones. I know that this minimal counterexample has to have at least 5 vertices in it. But what I want to point out here is that of all the other vertices in the graph, I won't be able to find one vertex that's adjacent to both u and v. There might be some that are adjacent to u. There might be some that are adjacent to v, but I can't find one that's adjacent to both u and v. Otherwise, I'd have a triangle, and my assumption here is that G is triangle-free, does not contain a triangle. So I'll say since G does not contain a triangle, sometimes I'll use this notation for a triangle, does not contain a triangle, there's no vertex adjacent to both u and v. Now I want to say something here about how big the degree of u and v could possibly be. So what I'll do here is I'm going to add up of all these, right? There could be other vertices here in the graph. I'll sort of focus in on these vertices over here, and I want to count these. So it's possible that u and v, that their neighborhoods are all of this thing, that the union of their neighborhoods is all of the remaining vertices. So there's n minus 2 vertices over here. And that would be accounted for by adding up their degrees. Less 1 because u and v are both adjacent to each other. So if I add up, if I take the degree of u minus 1, so just the vertices over here that u is adjacent to, add that to just the vertices over there that v is adjacent to, then I can't get more than n minus 2, right? Because there's only n minus 2 vertices over there. And so I'm doing some arithmetic here. I'd get degree of u plus degree of v minus 2, less than or equal to n minus 2. Add 2 to both sides. I'll see that degree of u plus degree of v is at most n. Now that'll be important later on. So like I said, the idea here is I'm going to take G, this minimal counterexample with respect to order, and I am going to remove u and v. I'll produce a smaller graph G prime. Let me maybe start with that. So I'll let G prime equal G minus uv. So I'm going to remove those vertices from G. And my claim is going to be that G prime has size at least n squared over 4, or rather its order squared over 4, so n minus 2 squared over 4. Notice this has order n minus 2. So it satisfies this hypothesis, and I want to show that it doesn't have a triangle. Well, that's pretty obvious. If G didn't have a triangle, if I remove 2 vertices, I can't create a triangle by removing vertices. So certainly G prime won't contain a triangle. So I can say it's order n minus 2. It's triangle free. So if I can just show that its size is big enough, then I'll have produced a smaller counterexample to the claim, which would contradict my choice of G as the smallest counterexample. That's the idea. That's how this proof works. So that's what I need to show. Is I want to show here. So let m prime be the size of G prime. I want to show that m prime is strictly greater than its order squared over 4. So n minus 2 squared over 4, take the floor. I'd like to show this. If I can do that right, then I'll have a contradiction. So let's see. So let's count the edges in m prime. M prime, well, it's however many edges were in G, but then I've removed u and v, right? And so I've lost all the edges between them. So I've lost everything in the neighborhood of u. I've also lost everything in the neighborhood of v, but I've actually double counted, right? If I do that, I've double counted this edge between them, between u and v, and so I have to add 1 to this. That would be the size of G prime, would be this. Now m, by assumption, is greater than n squared over 4. And degree of u plus degree of v, from what we showed above, it's less than or equal to n. So when I subtract that, it'll be greater than or equal to m minus n. So I can say minus n here, plus 1. So now we just need to play around a little bit and eventually get down to this claim. So let's see, how does that work? Well, if m prime's greater than n squared over 4, the floor of that, then it's certainly greater than n squared over 4. Let's find a common denominator here, right? So it'll be 4n over 4 plus 4. So this is the same thing as n squared minus 4n plus 4 all over 4. Just finding a common denominator between all of them. And then the top I can condense, right? This is the same thing as n minus 2 squared over 4. So I have m prime greater than n squared, n minus 2 squared over 4. Since m prime is an integer, we have that m prime is strictly greater than the floor of n minus 2 squared over 4. And so I'll write at the bottom, I've explained it, a couple times, but I'll say it again. So this contradicts our choice of G. Remember, G was supposed to be the smallest counterexample with respect to order, but we found that if we took G, we could find a smaller counterexample that satisfied all the hypotheses, was triangle free, its size was greater than its order squared over 4. And so what this means is that there was actually never a counterexample to begin with. There couldn't have been. Because if there was, I could have selected a smallest one, and this argument, wouldn't have worked in the same way. And so this proves the theorem. So again, what this is saying, theorem 1.9 here, is that if a graph of order n has size m at least or greater than n squared over 4, not only is it not bipartite, but now we know something more, that it also contains a triangle. It has to contain a triangle. All right, that's it for this video. See you later.